Welcome to the deep dive. Today, we're tackling something really fundamental, designing secure software.
Yeah, it's crucial stuff.
We've got this great book as our source, and the core idea is, well, security can't just be bolted on later.
Exactly. You can't just, hope for the best and patch it up. It needs to be baked in right from the start, from the design phase.
It has to be part of the blueprint.
Precisely. And the book we're looking at, it points out a couple of big challenges here.
Okay.
First, just how tricky security and trust really are in the digital world. They're subtle.
Uh-huh.
And second, this idea, this sort of misconception, that software development doesn't need that strict upfront design you see in, say, building bridges or something, which is just wrong.
Yeah, that seems like a dangerous assumption. So this baked-in idea, the book uses a really good analogy, doesn't it?
It does, the hiking trail.
Yeah, the one along the ridge. Some parts are easy, others are, right near a cliff edge.
Right. And the book is trying to be that guide, showing you where the path is safe and where the big risks are when you're building this stuff.
Okay, and a core part of that guidance is something called threat modeling.
Threat modeling, yes. It's fundamental. It's about shifting how you think.
How so?
Instead of just thinking, how do I build this?
Yeah,
You have to ask, how could someone break this?
yeah.
You need to think like an attacker.
Put on the black hat, so to speak.
Sort of, yeah. Do that early. Find the weaknesses before they become real problems.
And the book gives us a framework for this, the 4 questions.
Yep, the 4 questions framework, super simple, but powerful.
What are they again?
That's what are we working on?
Yeah.
Pretty basic.
Right.
Then what can go wrong? That's the key attacker mindset bit.
Uh-huh.
Then what are we going to do about it? The actual fixes or mitigations.
Right.
And finally, did we do a good job? Like checking your work. It's a cycle.
Constantly asking those questions.
Exactly. So that's what we'll do in this deep dive. We'll pull out those key design principles, look at common threats, and get into the strategies for mitigating them, all based on what's in this book.
Sounds good. Let's start with those design principles. The first one mentioned is economy of design.
Yeah, economy of design, it really just boils down to keep it simple.
Simple is better.
Absolutely. The more complex something is, the more places there are for things to go wrong, for vulnerabilities to hide.
Okay, so every extra feature is potentially another way in for an attacker.
Pretty much, yeah. Complexity is not your friend when it comes to security.
Got it. Next up is transparent design. Now, this one sounds a bit odd. Does it mean we, publish everything?
No, not your secret keys.
Mhm.
Transparent design means the security of the system shouldn't rely on the design being secret.
Okay, explain that.
Think about standard crypto algorithms like AES. Everyone knows how AES works. It's public knowledge,
Right.
but it's still secure because the keys are secret. If knowing how your system is built makes it insecure, then the design itself is flawed.
Ah, okay. The strength should be in the secrets, like keys, not in hiding the blueprint.
Exactly. That's a crucial distinction.
Then there's a cluster of principles under exposure minimization. Sounds like playing it safe.
It is. It's all about reducing the opportunities for attack or for harm if an attack happens. First under this is least privilege.
Least privilege. We hear this one a lot. Only give the absolute minimum permissions needed, right?
Precisely. The book uses that analogy. You wouldn't clean a loaded gun.
Right.
Same idea. Don't give software admin rights if it just needs to read a file. Limit the privilege, limit the potential damage.
Okay. And related to that is least information.
Yeah, pretty straightforward. Just don't expose more sensitive information than you absolutely have to.
Like overly detailed error messages.
Exactly. That can give attackers clues about your system's internals. Less info exposed, less for them to work with.
Makes sense. Then secure by default. This feels like it should just be standard practice.
You think so, but it's often missed. It means settings, options, APIs, they should default to the most secure setting.
Like browsers defaulting to HTTPS now.
Perfect example. Make security the easy, automatic choice. Users should have to actively choose less security, not the other way around.
Okay. What about allow lists over block lists?
Yeah. Think of an allow list like a strict guest list. Only people on the list get in.
Yeah.
A block list tries to name everyone who isn't allowed. That list is potentially infinite, and you'll always miss someone.
So it's better to define what is allowed rather than try to block everything bad.
Generally, yes. It's a much more manageable and often safer approach. You're defining the known good rather than chasing the unknown bad.
Right, you're not constantly playing catch-up. Then avoid predictability.
Yeah, don't make things easy for attackers to guess. The book uses sequential customer IDs as an example.
Oh, right. If they're just 1001, 1002, 1003. An attacker can just guess valid IDs.
Exactly. Use random, unpredictable identifiers for sensitive things. Don't be predictable in behavior either if you can help it.
And the last one under this umbrella is fail securely.
Super important. When things inevitably break or error out, they need to do it in a way that doesn't open up a security hole.
So if logging in fails, don't tell the attacker whether the username was valid or not?
Exactly that kind of thing.
Yeah.
Don't give away information even when failing. Default to a safe, closed state.
Okay, moving on from exposure minimization, we have complete mediation. Sounds thorough.
It means every single time something tries to access any resource, its authorization must be checked. No exceptions, no shortcuts.
Every single time.
Every single time. No trust assumed, no checks bypassed. Think of it like a bouncer checking everyone's ID every time they enter the club, no matter how many times they've been in before.
Okay. Then separation of privilege sounds similar to least privilege.
It's related but distinct. This is also called separation of duty. It means requiring multiple conditions or checks, ideally controlled by different people or systems, before allowing a sensitive action.
The safe deposit box analogy from the book.
Exactly. The bank has one key, you have the other. You need both. It prevents one person or one compromised component from having total control. 2 checks are better than 1.
Clear. What about least common mechanism?
This is about minimizing how much different parts of your system share. Shared resources, shared code, shared pathways.
Why is that bad?
Because if there's a flaw in that shared mechanism, it can potentially affect all the components using it. Think shared libraries or communication channels.
So keeping things separate limits the blast radius if something goes wrong in one part.
Precisely, like watertight compartments on a ship.
Got it. Then accept security responsibility. This sounds more cultural.
It absolutely is, but it's crucial. Security isn't just one person's job or one team's job.
Yeah.
It's everyone's responsibility.
The designers, the coders, the testers, the ops team.
Everyone. The book warns against that anti-pattern where everyone assumes someone else is handling security. That's how things get missed.
Yeah, dangerous gaps can appear there. And the last principle, defense in depth.
A classic. It means having multiple layers of security controls. If one layer fails or an attacker gets past it, there are other layers behind it to stop or slow them down.
Like a medieval castle. Walls, moat, guards.
Exactly like that. Don't rely on just one single defense. Layer them up.
Okay, that's a really comprehensive set of principles. Now, the book pivots to thinking about the threats themselves. We need that attacker mindset again.
We do. You can't defend effectively if you don't understand what you're defending against. You have to actively think about how things could break or be misused.
And that brings us back to threat modeling as the way to do that systematically.
Right. It's not just guessing, it's a structured process.
So how does that process work, practically speaking?
Well, the book breaks it down. First step, identify your assets. What are you actually trying to protect?
Data, functionality, reputation?
Exactly. User data, financial records, the ability for the system to stay online, intellectual property. And you need to prioritize them. What's most critical?
Okay, know what's valuable. What's next?
Identify attack surfaces. Where can an attacker actually interact with your system?
Like web inputs, APIs, network ports.
User interfaces, APIs, file uploads, network protocols, even physical access sometimes. You want to map these out and ideally minimize them.
So know what you're protecting, know where they might attack from, then
Then you identify threats. This is the core brainstorming part. How could an attacker exploit those attack surfaces to harm those assets?
thinking about specific attack types.
Yes, and thinking broadly. Not just direct attacks, but also indirect ones, maybe chaining vulnerabilities together. How could things go wrong across trust boundaries?
Trust boundaries where different parts of the system with different levels of trust interact.
Exactly. Like input from the internet hitting your core logic. That's a key place to look for threats.
And the final step in the modeling process.
Mitigate threats. Once you've found potential problems, you figure out what to do about them. How do you reduce the likelihood or the impact?
Which leads us nicely into mitigation strategies later. But first, the book gives us that STRIDE model to categorize threats.
Right. Yeah, STRIDE is a super helpful mnemonic. Helps make sure you're thinking about different kinds of threats.
Remind us what it stands for?
Sure. Spoofing, pretending to be someone else, tampering, messing with data or code, repudiation, denying you did something,
Okay.
information disclosure, revealing secrets, denial of service, making things unavailable, and elevation of privilege, gaining more access than you should have.
So spoofing is like a fake login page. Tampering is changing a bank balance. Repudiation is saying, I never ordered that.
Right. Information disclosure is reading someone's emails. Denial of service is crashing the website. Elevation of privilege is a regular user becoming an admin.
Got it. That covers a lot of ground. The book also mentions the gold standard principles for data protection, CIA.
Yeah, the CIA triad is fundamental. Confidentiality, keeping secret. Integrity, making sure data is accurate and hasn't been messed with. And availability, ensuring the system and data are there when needed.
Confidentiality, integrity, availability, the core goals.
They are. And then there's another set of 3 principles about how you achieved CIA.
Which are?
Authorization, who is allowed to do what. Authentication, proving who you are. And auditing, keeping records of what happened.
Okay, so authentication is showing your ID. Authorization is checking if your ID gets you into the VIP room.
Perfect analogy. We often shorten them to Auth-N for authentication and Auth-Z for authorization.
Auth-N and Auth-Z. Got it. And auditing is the logbook.
Exactly. A reliable, tamper-resistant log of security-critical events. Essential for figuring out what happened after an incident and sometimes for deterring bad behavior in the first place.
You can't investigate if you don't have the evidence.
Precisely. And the book touches on privacy, too, which is related but distinct.
How does that fit in?
Well, good security is necessary for good privacy, but it's not sufficient. Privacy is also about managing expectations, being transparent about data use, and respecting user choices. A lot of privacy failures happen when those expectations aren't met, sometimes due to security flaws, sometimes just due to bad policy.
Okay, so security enables privacy, but privacy involves more than just security tech.
You got it. Clear communication about privacy practices is key.
All right, we understand the principles. We understand the threats. Now, how do we actually stop the bad guys? Let's talk mitigation strategies. The book says prioritize, right?
Absolutely. You can't fix everything at once, and not all risks are equal. Focus on the biggest threats to your most important assets first. Get the most bang for your buck.
Makes sense. And one of the first strategies is minimizing attack surfaces. We mentioned this during threat modeling.
Yeah, it's both a goal of threat modeling and a mitigation strategy itself. Less code, fewer features exposed to the outside world, fewer open ports.
Yeah.
It just gives attackers less to shoot at.
Close unnecessary doors and windows.
Basically, yes. Then there's establishing trust boundaries. Define them clearly.
Those lines between high trust and low trust zone.
Exactly. And put strong controls right at those boundaries. Don't let untrusted data just flow into sensitive areas without being checked, validated, sanitized.
Okay. And related to that is isolating critical components.
Yeah, kind of like bulkheads on a ship again. If one part gets compromised, try to contain the damage. Limit how much interaction high-trust critical components have with less trusted parts. Sandboxing is a common technique here.
Run risky code in a safe little box where it can't hurt anything else.
That's the idea. Then, define and enforce access policies. This links back to Auth-Z.
Saying who can do what and making sure the system actually enforces it.
Exactly. The policy is useless if it's not enforced consistently everywhere. No backdoors, no exceptions.
Secure communication is obviously huge today.
Non-negotiable, really. Encrypt data in transit, especially over the internet. HTTPS is the baseline for the web. Protects against eavesdropping and tampering on the wire.
And secure storage for data when it's just sitting there.
Data at rest. Yeah. Just as important. Encrypt sensitive data stored in databases or files. Control who can access that storage. And have good backups. Secure backups.
Right. Backups are crucial for availability, too. Now, input validation. This seems like where a lot of attacks actually happen.
It is. So much trouble comes from improperly handling data that comes from outside the system. User input, network data, files.
SQL injection, cross-site scripting.
Yeah.
All that stuff.
All that nasty stuff. You have to validate and sanitize untrusted input. Check links, types, formats. Reject anything that looks suspicious. Decode it carefully. The book mentions Unicode complexities and homomorphs.
Characters that look the same but are different.
Yeah, attackers can use those for tricky attacks.
Yeah.
And definitely don't just stick user input directly into commands like SQL queries or file paths. Use safe APIs, parameterized queries, libraries designed to handle this.
Don't build commands from untrusted strings. Big takeaway there.
Huge. Then there's cryptography. Can seem daunting.
Definitely. Keys, algorithms.
The book covers the basics. Symmetric versus asymmetric encryption, digital signatures, key exchange. The key takeaway for most developers is use well-vetted, standard libraries and protocols. Don't try to invent your own crypto.
Please don't roll your own crypto.
Exactly. And use cryptographically secure random number generators, CSPRNGs, for anything sensitive like keys or tokens. Regular random numbers are often predictable. Also understand hashes and MACs for integrity checks.
Use the right tools for the job, built by experts.
That's the mantra. Then, security testing, you have to actually look for flaws.
Not just assume your code is secure because you followed the rules.
Right. Functional testing isn't enough. You need specific security tests. Fuzzing, throwing weird data at it.
Yeah.
Penetration testing, simulating attacks. Performance testing to look for denial of service issues.
Checking logs don't contain passwords, things like that.
Yes, practical checks like that. Testing error handling is also critical. Do errors leak information?
And all this leads into overall secure coding practices. Good habits for developers.
Yeah, it's a collection of things. Handle untrusted input carefully. We covered that. Watch out for integer overflows, underflows. Use safe types. Check boundaries.
That can lead to nasty bugs.
Very nasty. Manage memory properly. Avoid leaks like heartbleed. Prevent buffer overflows. Be careful with multi-threading. Use locks. Ensure atomicity to avoid race conditions. Beware of timing attacks. Use compiler warnings and static analysis tools that catch a lot of potential bugs. Write clear comments, especially for security code. Document your security assumptions.
And build reusable security libraries.
Yes, if you solve a security problem well once, package it up so others can reuse it safely, instead of everyone making the same mistakes.
Finally, the book mentions dealing with legacy security. That's a real-world headache.
Oh yeah. Old systems, old libraries, outdated crypto.
Hmm.
They can be ticking time bombs. You need a plan to identify them, manage the risk, and ideally migrate away securely. You can't just ignore them.
Okay, so those are the defenses. The book also highlights some common traps, security anti-patterns, things to avoid.
Right. Knowing what not to do is just as important. First is the confused deputy.
A what now?
Confused deputy. It's when a component with high privileges is tricked by something with lower privileges into doing something bad on its behalf.
How does that work?
The book uses an analogy. Norman Bates, actually, or think of a web server. A user might make a request that tricks the powerful web server into accessing a file it shouldn't, using the server's privileges, not the user's limited ones. The server is confused about who it's really acting for.
Ah, okay. The powerful component gets manipulated. What's another anti-pattern?
Backflow of trust. This is when a system trusts data or requests coming from a less trusted place too much.
Like assuming input from a partner system is automatically safe.
Exactly. Or the book's example of third-party hooks. You let some external code plug into your system but give it way too much access, trusting it implicitly when you shouldn't. Trust should flow from high to low, not the other way around without careful checks.
Don't let trust flow uphill without scrutiny. Got it. And the last one, security by obscurity.
The classic mistake. Relying on secrecy of how your system works, instead of making it fundamentally robust.
Thinking if hackers don't know how it's built, they can't break it.
Yeah, but that's a fragile defense. Secrets get out. A well-designed system should be secure even if the attacker knows exactly how it works, like with public crypto algorithms. Don't rely on hiding things as your main defense.
So, wrapping this all up, the big message is about cultivating a security mindset.
Absolutely. It's not a checklist you complete once. It's a way of thinking that needs to permeate the entire software lifecycle.
From design through coding, testing, deployment, maintenance.
All of it. Think about potential threats constantly. Apply the principles, use the mitigations, test rigorously.
And it's everyone's job, right? Not just the security person.
Definitely not. We talked about accepting responsibility. Everyone involved has to play their part. Developers, testers, architects, operations. Security is a team sport.
The book also notes that customers are expecting more now. Security isn't optional.
It really isn't anymore. Users are more aware, regulations are stricter. Good security is becoming a baseline expectation, even a competitive advantage.
Right.
Building trust is key.
And the book finishes by emphasizing that improving software authenticity, trust, responsibility, it's an ongoing challenge in our super complex, connected world.
It is. The threats evolve, the systems get more complex. We have to keep learning and adapting.
So to quickly recap our deep dive, designing secure software isn't simple. It needs a proactive, continuous focus. You need to identify threats, use solid design principles, implement strong defenses, and crucially, foster that security-first mindset everywhere.
Yeah, we've covered a lot of ground, really just scratching the surface of the details in the book. It goes much deeper into threat modeling techniques and specific secure coding practices. Definitely worth exploring further if this is your field.
Absolutely. Which brings us to our final thought for you, the listener. Given how interconnected everything is, how complex software is becoming, what do you think is the single most critical aspect of secure design that we really need to prioritize going forward? Is it threat modeling, secure defaults, developer education, something else?
It's a tough question with no easy answer, but definitely something worth pondering. We hope this discussion encourages you to think more critically about the security of the software you rely on and maybe the software you build. Thanks for joining us on the Deep Dive.